thing, I'm going to do the one on the left first here. And the first thing you want to do is check to see, is this a linear linear one? And the way to do that is to take the first two terms and subtract them. You get 64. And then check and see if you add the 64 to the second term, do you get the third term? Nope. Okay. So then it's not. So now the second thing to do is to divide the second term by the first term. You get 2. So now what happens if you multiply the second term by 2? Okay? Well, what happens is you do get the third term. So, hey, we're starting to make some progress here. Okay. And as you double check, yeah, each one of these, you multiply it by 2, there you go. So this is a geometric sequence with a common factor of 2. Okay? I mean, those are the steps. That's how you figure it out. Now, as far as the explicit equation is concerned, well, what have we got here? We've got 6 through 10, right? But I'd kind of like to know what happened before 6, 5 and 4 and the others. Now, since I know that you multiply by 2, if I divide by 2, I should get the fifth term, so it's 32. And divide by 2 again, I get 16. And divide by 2 again, I get 8. I get 4. I get 2. That's the sequence. 2, 4, 8, 16. So anyway, what's happening here? Well, what's happening here is that for each one of those, it's 2 to the x power. It's 2 to the 1 is 2, 2 to the 2 is 4. So now I'm double checking, and of course you can't see it. Here we go. Double checking. 2 to the 5th is 32. Right? Let's try 2 to the 8th. Actually, I don't know what that is. 2 times, it's 2 multiplied 8 times. So I'm really going to just double check this. So if I take 3 of them, I know 2 to the 3rd is 8. And that's 8. And that's 4. And I know 8 times 8 is 64. I'm still going to have to multiply that by 4. And 256. And look up to the top. Is that what I got? Yes. Okay. So the formula works. That's the point. If you can't plug things in and get what you need, then you don't have the right formula. Now the question is, what about the recursive formula? Well, the recursive formula just says, okay, if I start with 1, okay, and 1 is equal to 2, what do I do to this to get the next one? Well, in order to get the next one, you take the one that came before it and you multiply it by 2. That is the sequence. Does anybody have a question about that? Yeah.
I mean, I honestly understand the recursive formula pretty good.
Okay.
Just this I'm a little confused on.
What part confuses you?
Well, I mean, you put over here an equals 2 to the x power, or fx equals 2 to the x power. Wouldn't that just be the same as like saying fx equals an times 2?
The difference between a recursive and an explicit, okay, it's important to understand what they are. Recursive means you have a starting point and then you have instructions on how to find the next number. So in order to do a recursive, you need 2 things. The first thing you're going to need is a starting point. The one we just did looked like this. So A1 is 2. Okay. If I want any term, if I want to pick up any one of these terms, and I know what the term before it was, right, all I have to do is take the term before it, like I want the 5th term. Well, I have the 4th term. Multiply that by 2. Okay? That's recursive. I can get the sixth term now,
Multiplying the fifth term times 2.
right, by multiplying this by 2. If I want the 73rd term, I'm in trouble with this, because I'm going to have to sit all day and multiply and multiply and multiply and multiply. That's why there are explicit formulas. Explicit, well, what does that mean? That means all I have to do is tell you what term I want, right? What number in this column, and you can immediately tell me what the number is on the other side. Okay, so here, well, I can't very well say a to the a sub n times 2. What's a sub n? Doesn't mean anything, right? Okay, what I have to figure out is what's happening here each time. And the thing is, I'm multiplying by 2 over and over and over again. And when you multiply by something over and over and over again, right? If I were multiplying straight across here, if I were multiplying a whole bunch of 2's, what would you say to me?
Why not just put them all together 2 times? 8.
How could I rewrite this?
2 times 8.
2 times 8?
No, sorry, no, 2 to the power.
Right. You'd pop in there with an exponent, right? This is an exponential function because we're multiplying by 2 over and over again, and if I want to represent this, I actually have to take 2 and multiply it together some number of times, and then, you know, check to make sure that whatever my starting point was doesn't affect it. But in this case, the first one, I'm just multiplying by 2 once. The second one, I'm multiplying by 2 twice. The third one, I'm multiplying 3 times. The 73rd one, I'm multiplying 73 times. Oh, but I don't want the 73rd one. I just want the generalized form of this. So whatever number you give me from here, that's what I'm going to plug in to say that.
But then it's not always going to be 2. Sometimes it's going to.
Well, it's not always going to be 2, right? I mean, these could have been 3's.
Then it would be 3 times. Okay.
Right? And if my starting point was something else, I mean, what happens if my starting point was 5, right? And I multiplied that by 3, and then I multiplied that by 3, right? 3 and 3, and so my sequence now started at 5, okay, and got multiplied by 3 over and over again. It's still an exponential function, but different, and I'm still going to have 3 raised to the something power. I'm just not sure what. So I have to look sort of at the pattern here. Right? This is 5 times 3 to the 0. This is 5 times 3 to the first. 5 times 3 to the third, to the second, right? 5 times 9, that's 45, right? The next one's going to be 5 times 3 to the third. Right? That's what this one will be. What would that be? 135? Okay. But I was able to get that without looking at this first. I was able to get it explicitly. Now, what is the pattern here? The pattern for this one is I started with 5. We multiplied it by 3 over and over and over again, but not the first time. First time we didn't multiply it by 3. The second time we multiplied it once. The third time we multiplied it twice. The fourth time we multiplied it 3 times. If I were going to do the 73rd one, I'd multiply it 72 times. Well, look, the first time, 0. The second time, 1. The third time, 2.
Oh, it's always 1 down, yeah.
It's always 1 down, right? Well, what does that mean? That means this is going to be 3 to the x minus 1 power. So if I want the 73rd term, I'm going to take 5 and multiply it by 3 72 times. Does that make sense?
Yeah.
That's it. That's the whole thing. At least for exponentials. Still confused?
No, I get it.
Lovely.
A lot easier.
Good. Then it comes time to graph. Now, here's the thing about graphing. If you're going to have an origin here at the bottom, that's 0, 0. And so you have to have everything go from there by regular intervals. You can't just put the numbers there that you know you have to graph, and you can't just skip until you get to like 900 and then go from there. I'm just going to do these by 2s, and then going up the other way, since there are 10 spaces, I'm going to do those by hundreds. Okay? So we'll do the first one is 100, right? And I'm choosing this because I know that I have to have numbers that go all the way up to 1,000 something. So I want to make sure that I choose my scale so that the numbers will fit. If I go all the way up here, it should get to 1,000. So here's where 10 is. So here's where 10 is. That's 1024. Okay, so now what's 9? 9 is 512, and it's in between 8 and 10, so it goes in the middle there. 8 is 256, so that goes right here. 7 is 128. Now, I know what the graph of an exponential curve looks like, and it does look like this. It goes straight up from there, comes down like that, and then comes all the way down, but never actually hits the 0. Okay? So it looks like this. And let's take a look at this one. Okay? So, again, what I told you before, the first thing you want to do is take the second term and subtract the first term and see what the difference is. And in this case, the difference is 2. Okay? Now, if I take the second term and I add 2, do I get the third term?
Yes.
Cool. And if I take that one and I add 2, do I get the next term? Yes. Okay? So that means this is an arithmetic sequence, a linear function, with a common factor of 2. Now, again, I can go back here, right? If 6 is 11, right? F of 6 is 11. What's f of 5 going to be?
It's going to be 9.
Right. I'm going to subtract 2 this time. And 4,
7.
3,
5.
2,
3.
1, and 0?
Negative 1.
-1. Okay. I now have everything I need to graph this baby. What do you need to graph a line? You need coordinates, but what else did you learn? What other quick way can you do this? What's that? Slope, and what else do you need?
Scale.
The y-intercept, right? You can put things in this form, right? Y equals mx plus b. Okay? Where this is the slope and this is the y-intercept. What's the y-intercept going to be on this? -1, exactly, right here. And what's the slope? Remember, the slope is the same as the rate of change. What's my rate of change here? 2. So my slope is 2. Up 2 over 1, up 2 over 1, up 2 over 1, and there we go. And let's just double check this. This is 1, 2, 3, 4. This is the fourth one, and over here this would be 1, 2, 3, 4, 5, 6, 7. So my fourth term should be 7. Hey, and it is. Okay. And if I keep going up that way, all of these will turn out to be points on the line. So with an arithmetic sequence, a linear function, we actually have some additional background so that we can do this fairly quickly. And we know that the explicit equation for this is f of x is equal to 2 times x minus 1. The recursive means I know what the first one was. The first one was 1, right? Okay. And I know that for every other one after that, all I have to do is take the one that came before it and add 2. And that's the recursive. Anybody have questions about that? I mean, that's how you go from a table to figuring out what kind of function it is, to putting down the name of the sequence and the common factor, building the equations, drawing the graph. That's what you need to know how to do. Okay? Yeah.
How do you know that the y-intercept was -1?
Well, the thing is, I know that if 0 is here, this will be -1, right? Are we okay with that?
Yeah.
We subtracted 2 and 2, right?
Yeah.
Well, this is, if x is 0, what's y?
-1.
Boom.
Oh, it's just corresponds to like what the 0 is. It's like.
Right.
Oh, okay.
This whole line right here, the name of this line is x equals 0. Everywhere on this line, x is equal to 0. Y can be anything, but x is equal to 0.
And that would be y equals 0, right?
This one would be y equals 0, yes. But here, this is wherever x is 0, right, that's going to be the point on this line. So here, if this is my graph, the y-intercept is where x is equal to 0.
Literally where it intercepts in the y-axis.
Literally where it intersects the y-axis. Right, right, exactly. Okay. The words actually mean something. You know, I mean, sometimes you have to learn new definitions for words or you have to learn new words, but once you do, the words we're using actually describe what we're doing. Okay. Recursive means recurring over and over again, right? And that's what happens here with a recursive equation. I have to do it over and over and over again in order to get the sequence. Whereas explicit, right, straight to the point. Okay? All right. Let's take a look at this one. This one was the new one. This is the one we haven't done before. So watch what happens here. When I subtract 49 minus 36, I get 13. If I add 13 to 49, what do I get? I get 62. Well, that was kind of close, but not really. Let's just look. Here's 13, right? And here, right, I needed, what? I needed 2 more to get to 64, so this would have had to be 15. Okay? In order to get from 64 to 81, I need to add 17. To get from 81 to 100, I have to add 19. Well, now, instead of looking for a pattern here, we're looking at a pattern here. There's like a secondary pattern here. From here to here is 2. From here to here is 2. From here to here is 2. So using addition and subtraction, if you can find the differences from here to here to here to here, and after you do it, it turns out that this is an arithmetic sequence. In other words, there's a common difference here, 2, 2, 2. This is a completely new kind of sequence, new kind of function, and it is called a quadratic function. Okay? And that's how to recognize it in a sequence. Okay? That's how to recognize it in a sequence. All right? Now, so type and characteristics, well, all you had to write here was it's new, it's not one of the other two. And the characteristics, it goes up by a different pattern. Now, an explicit equation. Take a look at this. This is 6, and what is this? 36. Okay, so there's got to be a relation there. Is there a relation between 7 and 49? What is it? Right. And 8 to 64 squared. So in other words, whatever x is, I'm going to square it. And that's my function. That's the function. In this case, I'm taking x, and I'm multiplying it by itself to get my answer here. The recursive equation is a little bit more difficult because there's like a two-step process here in order to figure out how to get from one to the next. Okay. But with a recursive function, all I have to do is have a starting point. Okay, so in this case, let's take A6 as my starting point. A6 is 36. Okay? How do I get to A7? Well, I'm going to add 13. So I have to find some way to express 13 with 7. Because if I'm looking for the 7th term, here's my x, or my n. All right, well, I don't really know what it is, but when I move up 1 here, I'm going to move up 2 here. When I move up 1 here, I'm going to move up 2 here. So all in all, there's got to be some way to say this. Can anybody see what the relationship is between 7 and 13 and then 8 and 15? Yeah.
Those numbers times 2 minus 1 is that?
That's exactly right. So if I want the nth term, right? Like let's say I want the 11th term here, I have to take the term that came before and then add what? I have to add 2 times the term I'm looking for minus 1. So what would that look like over here? Well, I'm looking for the 11th term. Okay. I know the 10th term is equal to 100. If I take 2 times 11 and subtract 1, what do I get? 21. And if I add that to 100, I get 121. And that is 11 squared. This is, right here, the recursive formula for this. Okay? Now recognize this is the first or second time we've done this. So I don't expect this to be as obvious to you or as clear to you as the other two were. That takes time. You're being introduced to this. But you got to start somewhere. So we're starting here. Now, how do we graph this? Well, first of all, let's do this. And I'm going to use 2, 4, 6, 8, 10 as my my scale down here. And my scale going up this way, since I got to make it all the way to 100, I'm going to do this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, I'm going to do this by tens. So this will be 10, 20, 30, 40, 50, 60, 70, 80, 90, and then 100. Okay. Now, as I start to graph this, what happens? 10 was 100, right? 10 squared is 100. 9 squared was 81. 8 squared is 64. 7 squared is 49. 6 squared is 36. 5 squared is 25. 4 squared is 16. 3 squared is 9. 2 squared is 4. 1 squared is 1. 0 squared is 0. So this is going to come all the way down just like this and hit here. But now that I have an equation for this, I don't really need to stop there. I can keep going. There's -2, -4, -6, -8, -10. What's -2 squared?
4.
4. So we're coming back up. And -4 squared? 16. So I'm still coming back up. -36 squared? -6 squared? 36. Okay. -8 squared? 64. So every one of these points, right, because I'm squaring it, just becomes a mirror of the point that was on the other side. That's what the graph of a quadratic equation looks like. This shape, if you want to know, is called a parabola. Okay? But it's basically a giant U. Okay? Does anybody have a question about that?